Okay, so in this second electrolysis video, guys, we're going to look at the industrial process which allows us to take bauxite ore, which is basically a rock dug up or quarried out of the ground, and we're going to go through the process of purifying that ore and turning it into usable product. So if we look at the diagrams that I have on the board, what you'll see is on the very left hand side there, if I just move this out of the way, on the very left hand side what you'll see is the bauxite ore. So that is the rock, if you like, that the geologists or the mining company or whoever it happens to be will take out of the ground. Okay, so that's it there. It's that sort of rather red looking compound because of the presence of iron compounds in it as well, and that is where all your aluminium comes from. Now that, first of all, what we have to do to it is turning it into this compound here, and that's a rather nasty purification process, and this compound here is purified aluminium oxide. So within this there's some aluminium oxide, and we've got to purify it down, and essentially what we want to get out of that is the pure aluminium. Now if we look at the next slide across, the next picture across, we now have our pure lump of aluminium which has come originally from the bauxite ore, and finally we then have it turned into something of some use. So these are the very expensive aluminium bifold and trifold doors. Okay, so that's what the manufacturer wants. They make those, they sell those, and they make their profit on them. So what we need to do is understand the chemistry behind how we actually get this aluminium from our ore, and how the properties which then allow it to be used for doors. And so what we have here is just a picture from inside an aluminium electrolysis factory or plant, whatever you want to call it, and you can see it's a fairly big, heavy, unglamorous industry. And what we're going to do is we're going to look inside these cells and see what actually goes on. What you'll see here are the anodes, big lumps of carbon is what they are, and they're attached to these rods which allow them to dip into the electrolysis chamber. So they're just being transported to be put into one of these chambers that you can see in the background. And these electrolytic cells, these electrolysis chambers, run 24 hours a day, 7 days a week, 365 days a year. They're never allowed to cool down, because if they did, all the substances within them which simply solidify, and that would be an absolute disaster in terms of getting the stuff out of the electrolysis chamber. You'll see this thing here hanging down, and that's where the aluminium oxide and all the ingredients for the electrolysis process basically come from. This machine runs up and down the full length of the plant, and it drops in a new charge of aluminium oxide and anything else that's required for the electrolysis process to take place. So it's a big, heavy industry, but we're not so much concerned with that. We're going to look at what's actually inside these electrolytic cells. So we're going to look at this diagram, if you like, of what we've just looked at there now. So let's have a look and see if we can work out what's kind of going on. So from our bauxite, which is basically the rock, but we have, through a purification process, produced aluminium oxide. Now, you should know by now that aluminium oxide is made up of aluminium ions, which are 3 positive, and oxide ions, which are in group 6 oxides, 2 negative. Now, per aluminium oxide, there must be 3 of those. So what we want to get to, fairly obviously, is pure aluminium. So no charge on it. So what's going to have to happen? Well, we should already know. It's going to have to gain 3 electrons. This will turn into oxygen, which you hopefully know is diatomic. Okay, and if that turns into that, okay, we have 3 O's over here, so we can only have 3 O's over here. Okay, so it's going to have to be 1.5 O2, and in order for this to happen, well, what's going to have to happen, it's going to have to lose electrons. We've 2 electrons, and each of these has to be lost. We've got 3 of those in total, so it's going to have to lose a total of 6 electrons, meaning that this is the oxidation process, and this is, of course, the reduction process. What I should have done there actually was that should be 6 electrons, and you can also see the number of electrons lost and gained should be the same. Okay, so let's have a look. Well, what we see here, first of all, is what we should say. So we have our graphite anode. Okay, and the anode will attract the anions, and the anions are the oxide ions. So what we will get here are the oxide ions being attracted to this, and you'll get very simply bubbles of a colourless, odourless gas. That would of course be the pure oxygen being produced. If we look down here, what we see with the aluminium, well, with the aluminium down here, okay, you will of course get a silver molten solid. Right, so and that molten solid is simply through here, just topped off. Just open a big tap, the molten aluminium pours out, they collect it into moulds and they solidify it from there. So we have a steel casing, and we have graphite or carbon anodes and carbon cathodes, just because they're relatively inert. In this case, actually, the anode here does actually take part in the reaction a little bit, and we'll look at that in a second. And they have very high melting points, these, which is important here because the temperature that this runs at is about roughly between 900 and 950 degrees Celsius, so it gets very, very hot in here. Now, the first thing that we have to do with the aluminium oxide here is we have to get the ions free. Now, melting that is very difficult. You're talking at well over maybe 2000 degrees Celsius, so it's extreme heat. So we cannot do that because it would become economically unfeasible for that to happen, and it would be very difficult to actually make a steel casing and make a casing out of a material which wasn't prohibitively expensive to get this stuff into its free ions. Okay, so how do we do it? Well, we've got to get it into its free ions in order for electrolysis to occur. So what we do is we dissolve it this time in this compound called cryolite, which actually isn't used very much now at all because world sources of cryolite have been depleted to such an extent that we use a different substance these days. So we have molten cryolite, which dissolves the aluminium at way below its melting point at 900, and that means that first of all we have free ions, so it will allow us to conduct electricity and conduct electricity very well, and it reduces the expense of the whole process by running at a much lower temperature than well over sort of 1500 degrees C. So what happens? Well, first thing that happens is that our aluminium is attracted here to our cathode, and when it gets there it picks up the electrons and it turns into pure aluminium. That's fine. Second thing then is our oxide ions, come here. They deposit their electrons onto the positive electrode, okay, or anode, and in doing so they form oxygen. Now that's not quite the end of the story here, because when the oxygen forms O2, oxygen gas, what happens is that it reacts with the graphite anode, which is made of carbon. Now, normally that wouldn't be a big deal, but because it's so hot in here, 900 degrees Celsius, hotter than a hot blue Bunsen flame, what happens is that they react together to give us carbon dioxide, which is a gas. Now that, you may think, is not a big deal, apart from the fact that it's a greenhouse gas, but what happens is your solid graphite anode turns into carbon dioxide gas. In other words, it erodes away. Okay, it is no longer there. You have to replace these things on a frequent basis, and that's quite expensive. You saw on our picture there earlier the big lumps of graphite waiting to be put into our electrolysis chamber. Okay, so this was them down here, and these are replacement anodes for the anodes which are worn away by essentially what is a burning away of the anode, because it's being turned into carbon dioxide gas. So that's a problem. Now, next thing then is, well, if you look on one of these electrolysis chambers, you'll see a layer at the top here. Okay, I'll draw it in as best I can. You'll see a layer in here of quite solid aluminium oxide, and you might say, well, why do they not take that aluminium oxide and push it down into the electrolysis chamber, make it molten, and turn it into your desired product of aluminium? Well, this actually acts as a layer of insulation and keeps the heat in. So they're quite willing to sacrifice the loss of a little bit of aluminium oxide at the top here to act as a thermal blanket, keeping the heat in, and that means you don't have to heat the process as much. So that is pretty much electrolysis of aluminium oxide. turning it into pure aluminium. It's a very expensive process because aluminium, first of all, is in a very high demand. Secondly, the amount of electrolysis that is involved in this is absolutely huge, and the amount of heat to keep this process going 365 days a year, 24 hours a day, is also extraordinarily high. The cryolite is another expensive thing. It is running out. They've had to find alternatives which are not cheap as well, but the whole process is good because you get, at the end of the day, your pure aluminium, which is the desired product for making your window frames, your doors, aeroplanes. What's the good thing about aluminium? Well, it's very unreactive. Okay, it's very light. It's a very good conductor of heat and of electricity. It can be bent into lots of shapes. So therefore, it's a very, very desirable product, and lots of companies will want to pay premium dollar to get their hands on pure high-grade aluminium, and this is the process which is used to do it. I hope that helps you with your understanding of the electrolysis of bauxite and turning it into pure aluminium.